Thank you. Mostly they're used in standby and emergency service. They're not of a size that you would want to have for regular utility service. We buy engines in the 0.5 megawatt to the 5 megawatt range generally. And we put these into facilities that are kind of remote that may have power outages at any time. They're used to supply emergency power so that heating and ventilation takes place, and whatever emergency systems that the plant deems are necessary are allowed to continue running. Usually that will be the control systems for all of the equipment. So standby gen sets, they can either be diesel or natural gas or gasoline fueled. And they're generally very quick starting. 20 seconds from the time that you get a start signal until you're up online accepting load is not at all unusual, and generally 12 seconds is about the time frame that you're looking for. But they have very large footprints, and they're heavy for the output, and they're high maintenance. We talked about reciprocating engines a little bit last time, and this is just adding a generator to it, which doesn't improve its reliability at all. So this is what you're going to look at when you get a package like this. You'll have the engine with a set of air filters just upstream of the turbos. You'll have a big radiator for cooling the water that cools the engine. And the generator will be attached, directly coupled to the engine with a small control panel and a terminal box for the electrical wires to be connected to take the power away. Generally, we buy them inside an enclosure because they're fairly noisy little animals, and we can't meet the 85 dBA noise requirements that OSHA has for occupied areas without an enclosure. And so this is an enclosure we used on the CNRL project. We have the airflow is inwards and upwards across a set of dampers, which are designed to maintain a reasonable temperature inside the enclosure. Across the engine, cooling the engine across a big radiator, and then out a discharge duct which has noise attenuation and takes the hotter air and just ducts it straight upwards into the atmosphere. The engine sits here, the exhaust is up through a silencer and then through the roof and out, and then the generator sits here. On the CNRL job, we asked that the genset power terminal box be mounted up high and on the side so that we can just come in through the side of the enclosure to pick up the cables rather than trying to stub up through the bottom. This type of a system will usually have a day tank in the skid that it draws its fuel from directly. And then depending on how long you need to run, you anticipate needing to run the engine before utility power can be restored, you may end up having a larger fuel tank situated outside somewhere with some kind of a transfer pump or a gravity feed system which will supply fuel to the day tank as the day tank fuel is consumed. One thing that's important to remember about the diesel engines is that they take fuel, they pump it up to a high pressure, and send it off to the injectors that are inside the cylinder heads, which actually injects it at the pressure required to overcome the compression of the cylinders. But they also use that fuel for lubrication of the injectors and for cooling of the injectors. So about 40 to 50% or more of that fuel gets heated up and is put back down into the day tank. So for installations that don't have a day tank, that excess fuel overflow has to go back to wherever that main tank is going to be, which could be some distance away, and then the small pump that's used for raising the pressure on the engine may not be suitable for that. That's why it's important to try to have a day tank somewhere nearby that the fuel can come from and then be returned to. Now as a package, we can get it, the genset with a control system which will do protection and monitoring of the engine and the generator, but we can also buy the package with the switch gear and the synchronization panels which allow it to be brought online to utility power if you should ever want to run this with utility power. And sometimes the operators and the owners like to do that so they can exercise the generator every month or so to make sure that it operates properly and that there's no carbon buildup inside of the cylinders. And while the unit is designed to be operated when utility power is off, it does need to be resynced with the utility power to transfer the load back. Usually facilities are going to have what's known as an emergency bus, which has all of the important loads put onto it. And as soon as the utility power fails, there's a breaker that isolates that emergency bus from utility power. Well, the standby generator comes online and then powers that utility bus. And they break that so that you're not asking the standby generator to power the whole rest of the facility. So now you've got your emergency system being powered by the genset. At some point in time, utility power gets brought back on. And so now you've got the whole rest of the plant operating on utility except your emergency bus. And now you have to bring the two back together again and get them in phase so that you can do a semi-seamless transfer of power, and then you can take your generator offline. So that's what the synchronization panels are for, is to bring the phases together so that you can bring the electrical power systems together.
So in case of power failure, the generator can auto start, or you have to go manually push the button?
You can set it up either way, but generally they're set on auto start. What the signal normally is, when utility power drops and the bus the breaker that ties the emergency bus to utility power, as soon as that opens, that gives a signal to the diesel genset to start. That way you don't accidentally start it when the utility power is still on. But to exercise it, there's also a manual start capability on them so that you can bring them on and offline whenever you need to verify operation. Make sure that maintenance operations you've done haven't compromised the operation of the machine. Okay, it requires a local date tank, possibly a larger external storage tank. Instrument air systems. Well, they're critical to most every plant. I haven't seen too many plants that don't use air as part of actuation systems for valves, especially isolation valves, your shutdown valves. And so we'll buy air systems to either supplement existing air systems or new systems to put into new facilities. And so we'll use either a reciprocating or a screw type or a centrifugal type of compressor depending on the flow rate required. If it's a small plant or it's an existing plant that needs a small supplement, then we'll go with a reciprocating kind of compressor. Relatively inexpensive, but we're not talking very high flow rates and very high pressure ranges here. So a small machine is a good fit, and because it's relatively small, it's not going to put a whole lot of pulsation into the yard piping, and so we don't necessarily need to do an acoustic analysis to verify that we're not going to have vibration in the yard piping. If we're talking higher horsepower and higher flow rates, then we'll go with a screw machine, at which point we would go with a packager, and there's several packagers that put out a very nice system that comes in its own enclosure. It doesn't actually look like a compressor. It's just a very nice looking enclosure that holds the motors and the compressor and whatever oil system is required and some, the air cooler for the discharge air. And if we have extremely high flow rates where air may be used for more than just instrument air, maybe a process air, or it may be used as utility air, and they're very high consumption users, we'll end up with a multi-stage centrifugal compressor. So they come with packages with dryers. Air is wet, humidity, and the instrument air system generally want extremely dry air, especially if you're in regions which get below freezing temperature. If you have water in your air system, it'll eventually work its way to a low point and sit. But if it freezes, it acts as a blockage, and now your air system won't be supplying air to the downstream users. So what you have to do is you need to dry the air to a dew point below whatever your local ambient minimum might be. So for an Alaska with a minimum of -40 or -50 Fahrenheit, we would always have our instrument air spec'd out to be -60 to a -100 degree Fahrenheit dew point. That avoids any complications of having ice formation in instrument air systems. And we can get it with receivers if we want to. Here's a package made by Kobelco. The actual air compressor is located within this box. It's very attractive packaging. They've done very nice on these things. It comes out, it goes into what they call a wet air receiver, which is just the air that hasn't been dried yet. And then we have a dryer set. This is a desiccant bed where air flows across the bed, and since it's a desiccant, it has a high affinity towards water, and the water gets trapped inside that bed, and out the top comes air that's extremely dry. Now the reason there's two here is because eventually one bed gets filled up and saturated to where it will no longer meet the dew point requirement that we have. And when that happens, the control system will automatically swap the airflow to the secondary bed, and then it'll be dried as it goes through this bed. Now this first bed will need to be regenerated so that it can be brought online when the second bed gets saturated. And that's done by a bypass, which bypasses dry air through the desiccant bed and purges all of the water out of it into a drain system. So in this way, by swapping back and forth between these two desiccant towers, you can continually supply whatever dew point air you have at whatever flow rate you need, just by varying the size of the compressor, the receiver, and the air dryers that you have. This is how it works. Moist air comes in, gets trapped in the desiccant, and then the purge air will come along and then purge the water that's out so that the desiccant becomes dry again, ready for use when the first tower starts to get saturated. The amount of purge air depends on the process of the desiccant that's being used. And Kelly, you're looking at on, what, about 18%, 18% for the instrument air compressors you were looking at? So it's about, yeah, between 14 and 18% is the maximum amount of air that's used for drying of the desiccant bed. There are some that have internal heaters so that you only have to use 1 or 2%. They keep the desiccant hot enough that it will reject the water extremely quickly when the flow is reversed, so that you have dry air coming out the discharge. There's another package. Again, you have a wet receiver, the dryers, and then you actually have a dry receiver, which is what feeds the rest of the plant. And the reason that you have the receivers is you have a volume chamber to allow some time from as you go from your high set point to your low set point on pressure, and it avoids rapid cycling of the compressors. Now when you size the compressors, I mean, there's an art to it, and then there's a lot of guessing to it in some instances. You look at your P&IDs, you come up with the number of users as far as instrument valves, nitrogen generators, utility requirements, and you can come up with a pretty good estimate of what the overall consumption is going to be. At the start of the job, it is an estimate, and we generally ask that there be a pretty healthy percentage addition onto that, because very few plants have ever required less air as they develop. Usually they all require more. And so we'll add 30 or 40% onto the initial estimate to come up with the sizing requirement for the instrument air compressor. And if everything works well, then the air compressor will work on about a 75% cycle, which means it'll run 3/4 of the time and then shut down for about 1/4 of the time. Well, it builds up pressure inside the receivers, and then it shuts down, and then as the air is used and the pressure starts to drop, when it drops down to the lower set point, usually about 80 psi, the compressor will start up again and regenerate and refill the air receivers. If we ever get an instance where the air compressor is running 100% of the time, that means that we've undersized the air system and that we need to reevaluate what the users are doing. Perhaps there's some user on there which shouldn't be, but it means that additional equipment needs to get bought. Because these are so critical, we'll normally buy 200% trains. So we have one in operation, and then one is a standby ready to jump in case something happens to the first one. And if the air consumption is such that it matches the one train capability, that means it's running all the time, where rates are pretty high, maintenance costs are going to be high, but it also means that if any other utility user comes on, you have to start the second backup machine to satisfy the needs of the extra air consumers, and so you no longer have any redundancy, and you have no longer any ability to swap back and forth or take a machine offline to do work on it while the other one picks up the load. So we always want to have about a 75% duty factor on these compressors.
Do you usually cycle them when you have two trains? You get even wear, or have a primary and secondary?
That's a decision that the operators are going to make, and in general, yeah, they will try to even the hours out. Once a month, they'll swap from A to B, and then next month they'll swap from B back to A, and they'll try to equalize the number of hours. I think that they would probably want to have one machine that has maybe 30% more hours than the other, because that way you know which one is going to be requiring maintenance first. And so you can anticipate that. And when it shows signs of maintenance requirements, you can go ahead and swap over, because you've got a pretty long period before that second machine may hit those same number of operational hours and then require that same maintenance. Big facilities like Alaska up in Prudhoe Bay, they've got 9, 10, 12 compressors all in instrument air service. And so instead of having 200% trains, they've got 12 30% trains. And so they have a lot of redundancy, but they also have a lot of users, so being able to keep them operational is real important to them. Nitrogen generators. With the advent of the dry gas seals, their need for nitrogen has kind of gone up in plants. We never heard of these 20 years ago when I was starting out, but now they're common everywhere. And there's two different types that we deal with. One is the reverse osmosis, and the other one's a pressure swing absorption style of PSA. Both of them will provide up to 99.9% nitrogen. They'll also provide lower purity levels if that's what your process requirements are. And this 5-to-1 ratio of instrument air to nitrogen, which means that for every 5 SCFM of air, you'll get 1 SCFM of nitrogen. If you don't need 99.9%, this will drop down to 3 or 4-to-1. But for what we do, since we're using this nitrogen in our seals, where we know there's processed gas and we know that there's spinning metal, which potentially could have a spark at any time, we generally demand that we have a 99.9% nitrogen to eliminate as much oxygen from a potential explosive atmosphere as we can. It uses instrument air on both of these. They're both passive devices. There's no moving parts on them. The reverse osmosis, you pass the air through a tube, the semi-porous tube, and it turns out that the oxygen, water, carbon dioxide, argon, helium, all pass through the tube at a higher rate than the nitrogen does. And so at the end of the tube, you end up with 99.9% nitrogen. The pressure swing absorption system uses a bed, a special carbon, I think it's a carbon material, which actually has an affinity towards oxygen. And as the air is pushed through it, the oxygen absorbs into the bed and is retained there, and so you have pure nitrogen coming out the other side. Because it uses instrument air and there is a pressure drop, your pressure is only going to be between 70 to 90 psi. So if you need higher nitrogen pressure, you need a compressor to take it up to whatever pressure level you're after. So this is the reverse osmosis style. Compressed air comes in, oxygen, CO2, carbon monoxide, anything else comes out, including water. And then out the ends of the tube is just nitrogen, and argon. So because of that, you have very high purity nitrogen. You also have extremely dry nitrogen, very, very minimal water content inside of there. And the PSA, compressed air comes in, gets absorbed into the bed, the carbon molecular sieve, that's the term. And then high purity nitrogen comes out. They're both sensitive to oils and water contamination, which is why we're using instrument air. You don't just hook it up to any air compressor. But it's very, very clean, a very low dew point. Controls. Actually, this is a fairly typical control panel that you would see in a lot of the facilities that we've worked in. It's in the central control room. The controls that we deal with are on the machine. And so those, they could range in sophistication. For a small centrifugal pump, you may just have a start-stop button or a handoff auto station that's near the pump. And in some instances, you may actually have an interlock with an isolation valve so that you don't start the pump with a block discharge, just a simple way of protecting the pump from being damaged. But if you have a complicated skid, gas turbine, steam turbine, compressor, large pump that may have a lube oil system that goes along with it, then the skid will come with a panel to control, monitor, and protect the equipment. And very large packages will come with a panel that's dedicated to the same control, monitoring, protection, and the process control. This is generally going to be a large compressors package. Some safety and shutdown features will want to be done by Worley-Parsons, or will be done by Worley-Parsons if directed by the client. In some cases, the client says we want to have our own dedicated safety integrated system that all of the shutdown features get wired to instead of the vendor's control panel. And so we have an interesting situation sometimes where we have to split signals so that the vendor panel and the safety system both work in parallel with each other. We always use a fail-safe electrical system, which means that all the instruments are going to have a fail-safe position, which means that they're going to be, the valves will be spring-loaded to go into what we consider the fail-safe position. If it's a process valve, it'll be fail-closed. If it's a lube oil control valve, it may be fail-open to make sure that we have enough or more than enough oil getting to our bearings. The circuits are energized when in normal operation, and they're going to be de-energized to indicate that there's a problem or that an action needs to be done. And in that way, if we have a positive signal for something, is when something is normal, and we take away that signal, that means that if for some reason we should ever have a wire break or a wire come off of a terminal, we'll end up shutting the machine down rather than having a shutdown protection device no longer functioning if we had a energized to indicate a problem system. Some clients actually do want to have it the other way. They want to have it so that you have an active signal, specify a shutdown, because that will decrease their accidental shutdowns because of wiring problems and broken instruments and things like that. But we don't generally, we would never do that initially. We'd have to have direction from a client to do that. That's a less safe system for the equipment. So a long time ago, these are what were considered the program interrupts and the reprogramming tools for the control technicians, because back 20 years ago, 27 years ago, control panels were all relay logic. It was before computers. And it's not unreasonable to expect that the control panels have evolved in parallel with the computer. So relay logic back in the 80s, and nowadays they've got the programmable logical controllers, the PLCs, which are infinitely small and infinitely more capable of anything that people had back when this machinery was first starting to come out. The one thing that's been common, though, is the programming language, which is known as a ladder logic programming language. Ladder logic came out of the relay system, where you could see each rung of logic and exactly how each relay reacted to it. And then as the PLCs became popular, the PLC manufacturers came up with a software programming package that just mimicked ladder logic, so that the people who grew up with the relay logic could transition easily into the new PLC style. Now, progress on the control systems has been fastest in the area of the lowest reliability. So, the panel logic control, relays are about the least reliable thing that you can get for controls. Mechanical devices, they physically have to move, make contact. Corrosion will prohibit them from working. High cycle fatigue will cause failures inside, which will prohibit them from working. Vibration may actually move them within their slots so that they're no longer in electrical contact with wires, which will prevent them from working. So there's all kinds of ways that relay logic could fail. And so, of course, the PLCs evolved fastest. So we came to microprocessor-based control systems. Big step up from relay logic. Now, when they first came out, they were a simplex system. There was just one PLC that ran everything. But because they were relatively new, this is in the late 80s, early 90s, a lot of people were a little bit distrustful of just having one PLC governing their $20 million train of equipment. And so they wanted to have some higher level of reliability, if at all possible. So they ended up asking for triple module redundancy, which is called TMR, which means that you end up with 3 PLCs, all which talk to each other. And they all have the same program inside, and they all supposedly get the same input. So they all do the same algorithms, and they all come up with the same answers, and they constantly talk with each other, and as long as every answer matches, everything is fine. If PLC A comes up with a different answer at some point in time, PLC B and PLC C actually stay, with the same answer, and they agree with each other. These two take control. This one issues an alarm that says there's something wrong with the PLC. So it sounds like it's a pretty reliable system. You have to have some voting between them. And when 2 out of 3 agree, that's what happens. And if you don't get 3 out of 3, the operators are alerted that something's wrong with the control system. They're hot swappable, which means that if this PLC were to fail, you could go ahead and pull it out. These two would still control the equipment, and then you could put a new PLC card in, upload the program to it, and then bring it online, and it would then start talking and comparing answers with the other two. The other thing is, obviously, you can't have different programs in these 3 PLCs, so you have to be able to upload new programs on the run. You have to take this offline, upload it, and then bring it online. It'll raise an error, but then you upload this one, and then these two will start to agree. Then you upload this one, and you end up again with all 3 of them being able to agree on how to control the equipment. Skid instrumentation. After the PLC was considered reasonably reliable and no longer the source of the majority of spurious shutdowns, they started looking at the skid instrumentation as the source of the majority of erroneous signals. So on the skid, we have analog vibration, analog signals for vibration and temperatures and flow rates. But we have switches, so digital signals for pressures and levels. And that worked really well with relay logic, because if you've got a close contact, you can work the relay really straightforward, but it doesn't work so well with PLCs. And transmitters don't work well with relays. And so the other problem that with switches is it doesn't announce that it's failed, generally. If you've got a switch for a pressure and something happens to it, wire comes loose inside, part of the mechanism breaks, it generally won't tell you that it can't work properly until you actually needed it. So for example, in my car, I've got an airbag, and I know that that thing runs off of a acceleration switch someplace inside the car. Do I know that's going to work? No, I don't know it's going to work because I've got a switch. Wiring problems could keep it from operating. Corrosion, I'm hoping that it works, but I'm not I can't count on it. Same thing with on-skid instrumentation. If it's a open circuit that has to close to cause an action, you don't know that it's actually going to do that until it physically does it, and that's when you needed it. You have no way of verifying it'll do that before that point in time, unless you go in this huge maintenance cycle of always pulling every switch off, checking it, and then putting it back in again. So the solution was, why don't we just put in redundant sensors with voting logic? We have redundant PLCs, we can put redundant sensors on as well. And so, up until that point, you had 2 pressure switches, one for an alarm and one for a shutdown. This one would go off, you get an alarm, that one would go off, the machine is shut down, pretty straightforward. So now they wanted voting logic controls. So you have one switch